Hello, in this video we are going to discuss about the assignment of the mathematical methods and physics that I had previously mentioned. I had completed the part A of that work. Now we'll be moving over to the part B where we'll be attempting various questions. I'm sure that you must have gone through the theoretical part of it, but if not, I'll be uploading those theoretical parts very shortly after I have made this video for your reference. You can take a look at that and understand the topic one by one. So the first bit has the question of the Cauchy's residue theorem, which is to be applied on this integral. Now, as far as the Cauchy's residue theorem is concerned, we'll not be discussing the detailed theory of it, but we'll definitely be obtaining the value over here, and the process that involves is simply going to be as follows. So first up, we take z is equal to e to the power I theta. This is the process, this is the way we do it, and for that we are getting dz to be equal to iz d theta on the left hand side there, or we have d theta simply to be equal to dz over iz. Onto this part on the right hand side we also have the value of the cosine theta to be equal to e to the power I theta plus e to the power minus I theta over 2, which goes to this value, which is 1 over 2 times of z plus 1 over z. And so we have the value of the integral over here to be coming out to be like this, that is 2 times of d theta, the value of d theta put over there, and then also the denominator with the 2 taken up as the LCM of 2 going and getting multiplied to that 2 over there, which was added to cos theta. Now for the unit circle consideration, we are taking the integral over the contour C, which is having z is equal to 1, the modulus of it. So this value that we have obtained over here is what we have obtained, we have rewritten over there. Considering the denominator for obtaining the poles, we have to obtain the roots. The root will be of this form, and with that root only the minus 2 plus root 3 is going to lie within C, because minus 2 minus root 3 would because root 3 has a value of 1.732, so minus 2 minus 1.732 will be minus 3.732, which is lying well beyond that. But minus 2 plus 1.732 is going to end up as minus 0.268, which is lying within that circle or within that region. So we are choosing that as the radius or that as the pole. Now with that residue available to us, not the radius but the residue available to us, we are taking for that single value of z, and we put here z minus of that pole value, and the denominator obviously is now has now been factorized into those two terms, which we obtained the root of over here, that is the root values, one plus and the other minus. Now calculations performed in that integrand, we get the residue to be this much. With that residue we put the Cauchy's residual theorem, which tells us to be equal to 2 pi I times of the sum of the residue, because we have a single residue over here. We have 2 pi I times of 1 over I root 3, which was the residue that was obtained. As you can see in the process, the entire process has been elaborately provided over there, and so we have the final result as 2 pi over root 3. So this is what we obtained over here. Now the next bit has asked us to show that the series infinite series, that is z to the power n multiplied to 1 minus z, converges for the modulus of z being less than 1, and we have to find the sum of it. Now to start with, we have to consider the D'Alembert's test. There are plenty of tests to check for the convergence and divergence of a series. This looks simple to me, where we can just consider un as the series, and with un plus 1 over un being equal to k, if the value of k is less than 1, then we'll be obtaining the series as convergent one. So let's check for that. Considering that if we take the limit n tends to infinity, now un plus 1, there's only one term containing n over there, which is z, the power of z, that is. So we have n plus 1 instead of only n at the top, and that is multiplied to 1 minus z, that remains as such, and down below for un we are putting as z raised to the power n times of 1 minus z. Obviously the 1 minus z's cancel out and the z to the power n's cancel out. That only thing that we have there is z, and z, as you know, the modulus of z is given in the condition that is provided to us, is that it is less than 1, so the series has to be a convergent one. Now we are supposed to obtain its value. Now as for the summation part, we have already obtained the value over there at the top. That is, we have seen that from the test we are getting this to be z, but that's the ratio part, but still that is the answer that we are going to get. So let's check for that. So this summation, I have extended the summation as you can see. So we have put the value of 1, 2 and 3 over there, and the series continues as such. Now we can take a common factor, that is z times of 1 minus z, from each of those terms, and what we are left with is 1 plus z squared, and it continues till infinity. And the series summation of that for an infinite series with the z factor being less than 1, or a fractional value, that is, we have that series summation as 1 over 1 minus z. We can obtain that from the Taylor series expansion. So 1 over 1 minus z, and you have z times of 1 minus z over there. So the 1 minus z's cancel out, and we just have the value to be equal to z. So that's the sum of the series provided to us. Here in the next bit we have to obtain the analytic function whose real part has been provided to us, is that u of xy to be equal to e raised to the power x cosine of y. Now that's the real part. If we have the imaginary part, then we obtain the entire analytic function, which is of the form u plus iv. So let's go for it. So we know from analytic functions about that is that we have to consider the partial derivatives with respect to x and y, and that is exactly what I have done there. So partial derivative of u with respect to x and partial derivative with respect to y, that is going to be equal to partial derivative of v with respect to y and negative of the partial derivative of v with respect to x respectively. And also for a given function v which is depending on x and y, we have dv to be equal to dv over del v over del x dx, partial derivative of v over y with dy. We are putting the values that we have obtained for the partial derivatives of u over there, because we have the condition of analyticity, and putting those values, what we get to know is that e raised to the power x sine y dx plus e raised to the power x cosine y dy, that is simply nothing but an exact differential form which is obtained over here. This is obtained over here as the exact differential form. And so from that, integrating that, we'll be getting this. Now this is a constant term c, which is the uh, arbitrary constant that we obtain out of integration, and z, that is the analytic function that we wish to obtain, is u plus iv. So u plus iv is the form, and v has the term c, which again I multiplied to that c. Let's take it as c primed over there. Now the bracketed term will have the things, will take the common term e to the power x outside of the bracket, and the bracketed term is quite familiar. It is e to the power iy, that is the exponential of iy, and so we have e to the power x plus iy, which is nothing but e to the power z plus c primed as the final result. So pretty straightforward case. All you have to do is obtain the imaginary from the real part, or the real from the imaginary part. That's the process that we carry out. There are also other processes which we may try, but this seems pretty handy.